So वहाँ पे बताया गया कि this is like fifth state of matter. Other states are like solid, liquid, and gas, and plasma is also a high energy state. So Bose-Einstein condensation is actually the Bose-Einstein condensate is actually a low energy state, जिसको आप फिफ्थ स्टेट ऑफ मैटर बोल रहे हैं. और ये कि अल्ट्रा लो टेम्परेचर करने पर जब हम लाइक 0 केल्विन के जितने नजदीक जा रहे हैं, तो ऑल द बोसॉन्स एक्चुअली कंडेंस टू ग्राउंड स्टेट एनर्जी लेवल, एंड सो बिलो ए critical temperature we form a Bose-Einstein condensate, and that critical temperature, that temperature that below which this condensate is formed is known as a critical temperature for Bose-Einstein condensation. तो लास्ट टाइम पे ये बताया गया था कि इसको एक्सपेरिमेंटली कैसे पाया जा सकता है. तो लोगों ने लेजर कूलिंग के थ्रू रुबीडियम में सबसे पहले 1995 में बोस-आइंस्टाइन कंडेंसेशन के ऑब्टेन किया, और इसका जो बेसिक प्रिंसिपल है, द बेसिक प्रिंसिपल ऑफ बोस-आइंस्टाइन कंडेंसेशन वाज एक्चुअली पोस्टुलेटेड बाय एस.एन. बोस. एस.एन. बोस ने जस्ट बोसॉन्स के बारे में और बोस स्टैटिक्स का फॉर्मुलेशन दिया, जो हमने बोसॉन्स के लिए बोस स्टैटिक्स का यूज करके वी हैव ऑलरेडी ऑब्टेन्ड द एक्सप्रेशन फॉर मीन नंबर ऑफ पार्टिकल्स ns बार. आइंस्टाइन बोस ने वो पेपर आइंस्टाइन को भेजा, आइंस्टाइन ने फिर उसका यूज करके इस स्टैटिक्स को का फॉर्मुलेशन किया. So Einstein used the ideas of S.N. Bose. So collectively, this is known as Bose-Einstein condensation. तो इस फॉर्मुलेशन में इन्होंने क्या किया था, we'll see. Yeah, how do you find the expressions for like Bose-Einstein condensation or तो वहाँ पे क्रिटिकल टेम्परेचर एंड क्रिटिकल वॉल्यूम ये दो टर्म आते हैं, तो इसका डेरिवेशन हम करेंगे और देखेंगे. तो यहाँ पे लास्ट टर्म पे ये बताया गया कि एट हाई टेम्परेचर्स द पार्टिकल्स आर रैंडमली मूविंग हियर एंड देयर लाइक ए बिलियर्ड बॉल, एंड द डिस्टेंस बिटवीन देम इज एक्चुअली क्वाइट लार्ज. जब हम लो टेम्परेचर पे जाते हैं तो उनका डिस्टेंस कम होने लगता है, और ईच पार्टिकल लाइक बिहेव एज ए वेव, and the wave is governed by de Broglie wavelength lambda, which is dependent on temperature. And when temperature is very low, then this lambda, which is de Broglie wavelength, tends to infinity, that is quite large. And in that case, the individual wave packets actually combine and make a big waveform whose lambda is actually quite large, and so below a particular temperature, if it has happened, then that temperature is known as Einstein critical temperature, and Bose-Einstein condensate is formed below that particular temperature. So last lecture पे हमने ये सीखा, और we derived the formula for Bose-Einstein condensation using the density of states. So we have used the expression for density of states, that number of states for bosons with momentum lying between p and p plus dp. You know this expression that dp dp is this. So वहाँ से you just formulated an expression in terms of energy, and in 3 dimension for bosons, this comes out to be this equation, which is dependent on epsilon to the power half. This was in 3 dimension, and then 2 dimension you can formulate it like epsilon power 0, that is constant. In 1 dimension it is epsilon power minus half. So Sanskar had asked like what happens at 0 dimension. So that was a homework for all of you. So 0 dimension mein it is like a delta function. You can just check that density of states for 0 dimension, that is like quantum dots. Discrete energy levels are only possible, so it is like a delta function. So using this expression for density of state, in 3 dimension. So we formulated the number of particle, the average number of particle, या total number of particle. We formulated the expression for that using this density of state. So this you know that this is the expression for an ideal gas. This is the mean number of particles. This is the expression that we know. Okay. So the total number of particles is nothing but the summation over all such states, I is equal to 0 to infinity, and then you tries to convert summation to this integration. Then GSLR, everything is similar to that. And now you put the value of the density of the state in 3 dimension, and so this is the whole expression. Equation number 3 that I've used many times. So n is equal to 2 pi v by h cube, and this other term is actually just you can formulate it in terms of d Broglie wavelength. So you end up getting expression which is dependent on v by lambda cube and some integration. This integration you will see that it is actually a special function. So the expression for the total number of particles n end up is simplified, and it is just v by lambda cube at a function that is a special function here that is dependent on a value alpha. So f3 by 2 and the alpha, where f3 by 2 alpha is nothing but this integration. यहाँ पे लिखा हुआ है f3 by 2 alpha is nothing but square root 2 by square root pi and this integration. Right? And it is, you know that it is dependent on alpha. तो ये आपको होमवर्क भी दिया गया था कि what happens when the value of alpha is changed. Let's say alpha is 1 or alpha is 0 or alpha is infinity, what happens? So you had to plot it. ये आपको होमवर्क में दिया गया था. यहाँ पर ये जो अल्फा है, अल्फा इज डिपेंडेंट ऑन ए प्रॉपर्टी which is related with chemical potential or absolute activity बोलते हैं इसको, or fugacity for a gas, and it is actually associated with chemical potential of the ideal gas, the gas we are discussing. So alpha, the value of alpha is dependent on mu, and when mu is tending to 0, so the value of alpha is just 1. And that is actually one of the critical values that will be required to estimate the critical volume or critical temperature. So this was your homework last time. I hope you have done it. That plot this function f3 by 2 alpha, f5 by 2 alpha, and so on. It is just a series, a special series. So f3 by 2 at alpha is equal to 1 is nothing but a zeta function, and the value is 2.6.2, and similarly zeta 5 by 2 is 1.341, and f infinity at alpha is equal to 1 is nothing but 1. तो ये आपको प्लॉट करना था. अभी भी अगर नहीं प्लॉट किया है तो ये आपको प्लॉट करना है. You have to check how to plot it. This is just a series. और ये सारे डॉक्यूमेंट्स मैं शेयर करूंगा आपको, तो इट विल बी इजियर फॉर. So using that expression, that n is equal to v by lambda cube, and then the function which is dependent on alpha. So there you estimated, you have found the expression for n. Find out. So it is here actually. So you found the expression for capital N, which is solving this derivation, And this, what is this function f3 by 2 alpha? If you just derive a series, just check it. So वहाँ पे जो expression था f3 by 2 alpha, और मैंने बताया कि it is nothing but this integration 2 by root pi 0 to infinity and this integration. So we had already discussed about it last time, and found out that this is actually a series of alpha, that alpha plus alpha square divided by 2 the power 3 by 2 and plus alpha to power cube 3 to power 3 by 2 and so on. So this was f3 by 2 alpha. So if you generalize this expression, so if you let's say forward like f5 by 2 alpha क्या होगा, तो यहाँ पे n की जो पावर है वो 5 by 2 हो जाएगी and so on. So in general, a function, a special function can be formed like fs, the suffix s, and alpha is nothing but alpha to the power n and n to the power s, where s may take any value, any value it can take 0, 1, 2, or half, whatever. Just you need to formulate this. So using this special function, we had derived the expression for the total number of particles, and it was found to be of this form. So यहाँ पे यह आया था कि n is nothing but v by lambda cube f3 by 2 alpha. So how to define the critical temperature? So critical temperature is a temperature below which all the particles condensate to the ground state, and this happens when alpha is actually maximum, or the value of mu is 0. Mu is the chemical potential, that is 0. So this happens at when alpha is maximum, that is 1. 1 is the maximum value of this alpha. So you replace f3 by 2 alpha to f3 by 2 1, and at t is equal to t0, this de Broglie wavelength is lambda 0. So n is nothing but v by lambda 0 cube f3 by 2 1, and this value is nothing but 2.612. So capital N is nothing but this expression. You just plug in the value of de Broglie wavelength, and you end up getting an expression for T0, where T0 is the temperature. So T0 is nothing but h square by 2 pi mkb, and rho is capital N divided by v. This is the rho, the density. Rho divided by 2.612 power 2 by third. So this you got the expression for critical temperature, and this is a temperature below which all the particles condense to the ground state. So but this was actually this was in the last one, but till now the expression that we have found, that n is equal to v by lambda cube and then function 3 by 2 alpha, this expression actually does not count the ground state particles. Why? Because we have some that how we have found the number of particles. We have found by converting summation to integration, and there in that integration the value of g epsilon, that is density of state, when for ground state, that is epsilon is equal to 0, since density of state was proportional to epsilon power half. So when epsilon, the value of epsilon is 0, so density of state is 0. So ground state is in this formulation we have not counted the number of particles in the ground state. अभी तक जो हमें मिला है with the value of capital N, that is actually the particles above the ground state. Here the particles in the ground state is not estimated, not counted, because we have changed the summation. That summation से हमने जहाँ इंटीग्रेशन में चेंज किया है, वो आपकी स्लाइड में चेंज किया था, आप देख लो. जब हमने शुरू में जब हमें यहाँ पर during the जब हम यहाँ पर n इक्वल टू लिख रहे हैं समेशन ni गोइंग टू 0 to infinity एंड, और यहाँ पर हमने इसको इंटीग्रेशन में चेंज किया, and this integration is g epsilon d epsilon divided by that. So but it does not take care of particles in the ground state, because when epsilon is equal to 0, since g epsilon is proportional to 3 epsilon power half, okay, so when epsilon is equal to 0, the g epsilon, that is density of the state, automatically goes to 0. So here the ground state particles are not being counted. All other particles other than ground state have been counted. So actually, the actual formula, we should add the number of particles in ground state plus whatever we have got till now. Okay. So at low temperatures, bosons tend to condense into a ground state, and the number of this state becomes very less than that of any other state. So अभी तक जो हमें एक एक्सप्रेशन प्राप्त हुआ था, वो एक्चुअली हम ग्राउंड स्टेट के अलावा जो पार्टिकल्स है उसको हम काउंट कर रहे हैं. द टोटल नंबर इज एक्चुअली, वी नीड टू ऐड द मीन नंबर ऑफ पार्टिकल्स इन द ग्राउंड स्टेट प्लस दिस वी हैव गॉट फ्रॉम द एक्सप्रेशन. Okay, so the total number of particle n is n0 bar plus this value, where this can be rephrased in terms of critical temperature. That is, it is nothing but n and t divided by t0 cos 3 by 2 and this value. Okay, so here n0 bar is nothing but the number of bosons in the ground state. Or फिर आप you can take the different cases. What happens when let's say this temperature is going to 0 Kelvin, yeah, tending to 0 Kelvin? So what happens? So in that case, you know that since n1 bar is nothing but 1 over exponential beta epsilon 1 minus 2 minus 1, and this value is actually quite less in comparison to this, which is the mean number of particles in the ground state. So here you have replaced epsilon by epsilon 0. Okay, so you need to replace n0 bar by this value, and at t going to 0, what happens? At t going to 0, this simplifies, this expression simplifies to so t going to 0, so n0 bar is nothing but 1 over exponential minus beta mu minus 1, and at t going to 0, it will be just minus kt by mu. मुझे पता है एक और चैट थी यहाँ पे. Okay. तो यहाँ पे आपको ये था एक्चुअली दिस वाज. So capital N is nothing but so t going to 0 की लिमिट में this that expression 1 over exponential beta epsilon minus mu minus 1, that turns out to be kbt divided by epsilon 0 minus mu. So you just replace n0 bar by that value, and so this is the whole expression. That this is the total number of particles, where this first term counts the particles in the ground state, and the other term counts the particle in the excited state. Okay, or when t going to t0, what will happen? This will be simplified. Yeah, when t is actually there, so there are now two cases. What happens when t is less than t0, and what happens when t is greater than t0? So we will see that when t is less than t0, the total number of particles is actually this n0 bar only, that is the particle in ground state, and at t greater than t0, this expression actually survives. So when temperature is above this condensate temperature t0, so you have particles in the ground state as well as particles in the starter state. But when t is less than t0, this term will vanish, and you will end up getting only the term which is responsible for that whole particle, all the particles are in the ground state. So this you will this you need to simplify it for both the things. both the temperature range, T less than T0 and T greater than T0. And then, so I will discuss first one, and this one is will be your homework. So just simplify. So by simplifying it further, you will end up getting so below what happens below T is 0, T less than T0. So the energy is 0 and the density of state is 1. And from there, you find out that mean number of particles is nothing but minus kT by mu. And when, so here mu is actually going to 0 or alpha is going to 1. So below critical temperature or critical volume, this value of alpha is actually equal to 1. So capital N is nothing but N0 bar plus this whole term. Okay, let's say N0 bar, the value of N0 bar is N0 and plus N. So here you can end up getting the expression for N0, which is N0 is the number of particles in the ground state. So you end up getting a formula that N0 is nothing but N1 minus T by T to the power 3 by 2. So you can plot, so N0 by N and T by T0, you can plot it. So you get a expression which is dependent on T power 3 by 2. So here you can estimate what happens when T is below T0. Okay, so this expression does not count. This expression is not valid because it will be negative, and you know that this number cannot be negative. So here you can just see this plot. Okay, so at T by T0, T by T0 is 1. Okay, so this will vanish. N0 by N will go to 0 here. Okay, and you will end up getting that below T less than T0, this expression is not valid actually, and you know that all the particles are condensed to the ground state. So using this expression, one can find also the what is critical value. So just like critical temperature, that a particular temperature below which all particles condensed to ground state, that is critical temperature. Similarly, critical volume, like below a particular volume, a critical volume, all that particles condensed to the ground state. So there as well, the value of alpha, that is 1, or the value of mu is 0, and there then you can find out the expression for total number of particles in terms of volume. So N is nothing but at critical volume, N is nothing but V0 by lambda cube, and this is Fc by 2 of 1. So you just you can simplify it even further and find out that total number N is nothing but N0 bar plus N into V by V naught and this function. So you end up getting an expression similar to that, similar to critical temperature. So N0 is nothing but N1 minus V by V naught, and the plot here is linear. You get a linear curve, N0 by N and versus V by N naught. So below this critical volume, okay, the all particle condensed to the ground state, while above it they are distributed to the excited states as well. So this you can also solve at different regimes, like what happens when V is greater than V naught and what happens when V is less than V naught. So this you need to check it. So this was all for Bose-Einstein condensation, and you need to check this formulation for different regimes, T less than T0 and T greater than T0. Similarly, for different volumes as well, like V less than B0 and part happens at V greater than B0. So I will send all these slides to you, all of you, and I hope. So there are like few more topics like ideal gas. So I have listed all of them. So I will send you the slides maybe. You know. Then because you have already studied it in your MSc classes, like ideal Fermi-Dirac gas, Fermi energy, what the expression for Fermi energy, how do you find that? You already have discussed, studied about it in your MSc classes. Similarly, the expression for internal energy in terms of Fermi energy that you have already studied. I will send you the slides. So just specific heat of metals using free electron theory. So you know that it is 3/2R, while it was estimated to be quite large. The value was quite large, and it is found experimentally that the actual value is quite small in comparison to the specific heat of metals found from classical theory. So how it is corrected? So वहाँ पे concept of like Fermi temperature आया, और so ये पाया गया कि the effective temperature is not T but T by TF. So ये इसके भी slides में I will send you, है ना. And then magnetic susceptibility of free electrons in metals. तो जनरली आप जानते हो कि लाइक क्यूरी टेम्परेचर क्यूरी फार्मूला जो है वहाँ से काई इज प्रोपोर्शनल टू 1/T, ये आता है. बट फ्री इलेक्ट्रॉन्स के केस में ये पाया गया कि नहीं, इट इज एक्चुअली इंडिपेंडेंट ऑफ टेम्परेचर. दैट वाज आल्सो बेस्ड ऑन दीज क्वांटम स्टैटिक्स. तो ये भी आई विल आल्सो सेंड इट. देन लास्ट में आएगा वाइट ड्वार्फ एट सेकंड लिमिट. So I will send I will upload actually. I will upload the PPTs on the e-Pathshala. You can just check it.